Hello everyone. So for today we are going to do two things. So the class is going to have two parts. In the first part we deal with symbolization in first order logic, and in the second part we are going to do a little bit of natural deduction in first order logic. Okay, so before we start doing symbolization, I want to do a couple of problems that involved using derived rules from functional logic. And the reason I'm doing this is that there are a couple of deductions on the homework which is due on Friday that involved using derived rules. So I thought it's a good idea to remind everybody how these rules work. Okay, so here we have a proof. We have one premise and our goal is to get to A and B. Error C. With the derived rules, usually we can start working from the top and we can just see what derived rule we can apply to the things that we have. And by doing that, we try to make our way toward the conclusion. Okay, so here we have not A or not B. What can we do with that? Well, if you look here at De Morgan, from not A or not B, we can get not A and B. So let's just do that. So on line 2, we can get not A and B. And the rule we are using is De Morgan, and we are applying it on line 1. Okay, now my goal is to get to a conditional. So it's a good idea to look at the rules that involve conditionals. And here we have this rule PMI that tells us that if you have the negation of a formula, the negation of A, you can get A arrow whatever you want, right? So here on the left, we have the negation of A and B. So we can get A and B arrow whatever we want. And in this case, we want C. So from not A and B, using PMI, we can get A and B arrow C. And the problem is done. So you just need to cite the rule here, PMI, and we're applying it on line 2. Okay, now let's do another one. So here we have 3 premises, and our goal is to get to D. Okay, so my idea here is this. Since I'm trying to get D, and D is here in this disjunction, I am going to apply disjunction syllogism at some point, which tells me that if you have a disjunction and you have the negation of one of the disjuncts, you can get the other disjunct, right? So if, for example, you have A or B and you have the negation of B, you can get A. Or you have A or B and you have the negation of A, you can get B. Right? So here, since I want to get D, I need to have the negation of not C, namely not C. And that is basically C. So if I get C, then I get not C, and from that I can get D. So C is here, and in order to get C, I need to have A arrow B. Okay, so just keep that in mind when you're working. Okay, now let's look at this next. We have B. What is it that we can do with B? Well, if you look at the derived rules here, look at this one, PMI, the first PMI. It says that if you have A, from that you can get anything arrow A. So since on this side we have B, we can get anything arrow B using PMI applied on line 1. So what should we put here? Well, obviously we're going to put A, right? So we want to get A arrow B from line 1. Now that we have A arrow B, we can use one of the basic rules, namely arrow elimination, in order to get C. Because we have the antecedent of the conditional. So using 2 and 4 and arrow elimination, we get C. Okay, now that we have C, remember we wanted to get the negation of not C, which is not C. So now that I have C, from that, using this rule, dn, I can get not C. I'm using dn on 5. Now, since I have the negation of not C, and I have not C or D, from that I can get D. And this is disjunctive syllogism, which tells us that if you have a disjunction and the negation of one of the disjuncts, you can get the other disjunct. So I'm using disjunctive syllogism, this rule here at the top, and I'm applying it on line 3 and line 6. Okay, the problem is done. So you just work with what you have and you try to apply the derived rules to them. Sometimes you need to use some of the basic rules as well. But that's basically the idea. There is not much to it. You just need to know the derived rules well and apply them to what you have. Okay, so that's for the first couple of problems on the problem set. The rest of the problem set deals with symbolization. And we did some symbolization problems last week, and we're going to continue to do some more this week. So just to remind you, I'm going to do a couple of simple ones first, and then we get to the ones that involve multiple quantifiers. Okay, so let's start with this one here, the first one on the handout. Here we have Becky loves someone who does not admire her. So the first thing to notice is that we're dealing with the quantifier sum. So we are going to use existential quantifier. And since we're talking about someone, we're going to use the domain of people. Okay, the next step, the restrictor and the main. So the sentence is about someone who does not admire Becky. That is going to be a restrictor. And the main predicate is Becky loves that person that we are talking about in the restrictor. So there is going to be our main, right? We talked about restrictor and main last time. The restrictor is the group of people that the sentence is about, and main is the thing that we are saying about that group. So here about the person who doesn't admire Becky, we are saying that Becky loves her. So that Becky loves her or him is going to be the main predicate. Okay, so when you are dealing with the existential, restrictor and main are going to be connected to an and. So here is how we do the symbolization. There is some x in the domain of people such that the restrictor goes first, and the restrictor is x does not admire Becky. So using a for admire, this means x admires Becky, and then we need to negate it. X does not admire Becky. That is going to be a restrictor. Then we have an and, connect this to the main, and the main is that Becky loves X. So using L for love, Becky loves X. And the order is important, right? So B goes first, X goes second. And that's the symbolization for this sentence. Okay, let's do another simple one just to remind you how things work. So we have everyone who likes Alex respects Sam. Okay, we have everyone, so we are going to use universal, and the domain is going to be the domain of people. Now, what's the restrictor here? What's the group that we're talking about? We're talking about everyone who likes Alex, right? That is our restrictor. And about them, we're saying that they respect Sam. That is our main. Now, when you have a universal, remember that restrictor and main are going to be connected through an arrow. So here is how we do the symbolization. We say for all x in the domain of people, and the restrictor goes first. The restrictor is that x likes Alex, right? So let's use L for like. X likes Alex. Use A for Alex. Then we connect this to the main predicate. And the main predicate is that X respects Sam. So using R for respects, X respects Sam. Now here for Sam, we need to use a lowercase letter A, one of the lowercase letters A through R. We cannot use S. So let's just use M. And that is the symbolization. So the way that we read it is that for all x, if x likes Alex, then x respects Sam. Okay. So that's the basics. You need to be able to identify the restrictor and main, and you need to know how to connect them. Now let's do some problems that involve more than one quantifier. So here we have every doctor cued someone. To deal with this kind of thing, you will still use the same principles that we used for the last two problems. Identify your main quantifier. The main quantifier here is every. We are saying something about every doctor, right? So we are going to use a universal. The restrictor predicate is doctor, right? We're talking about this group of people. And about them, we're saying that everyone cued someone. So this is going to be the main, and these two are going to be connected through an arrow. That's the overall structure. So we go for all x in the domain of people. So let me put the domain here. Because we have someone, we are going to use the domain of people. And doctors are people, so we are good. Okay, so for all x, now the restrictor is doctors, right? So for all x, dx arrow. And now we deal with the main. And the main predicate here is itself a quantified statement. Let me put it in English first, then I deal with it. So we are saying that x cued someone. That's the main predicate. Notice that our main predicate itself involves a quantifier, someone. Okay, so I'm going to use existential quantifier. And to say that x cued someone using existential quantifier, we say there is some y such that x cued y. Right? And notice that I'm using y and not x. And the reason is that we are in the domain, we are in the scope of this quantifier here. We talk about the notion of scope, right? That's the formula immediately to the right of a quantifier. So the scope of this universal quantifier is from here to here. So when you are in the scope of a quantifier and you want to introduce a new quantifier within the scope of the first one, you need to use a different variable. So that's why we cannot use x for this second quantifier. There is some y. So we use y for the second quantifier. You can use z or any variable that is not x. Okay, so put that back into the main formula and you get the overall symbolization. We're saying that for all x, if x is a doctor, then there is some y such that x cued y. Okay, let's move to the second one. Now here we have every doctor cued some patient, right? So we are dealing with every statement. That's the main quantifier. Again, the restrictor is doctor, and the main is queued some patient. So let's say that for all x, then we put the restrictor, doctor, then we use an arrow to connect it to the main, and the main is that x queued some patient. So let me put it in English, x queued some patient. Okay, notice that the main predicate itself involves a quantifier sum. Okay, now we need to deal with this second statement, execute some patient. And notice that this one involves a restrictor predicate and a main predicate itself. So here we are talking about patients in the second statement. So that's the restrictor predicate for the second one. And about them, we are saying that execute them, right? So I hope this is not confusing, but this execute is the main predicate of this second statement. And of course, we are going to use an existential. So the way we do it is that, remember, we need now to use a new variable because we are in the scope of the variable. We are in the scope of for all x. So I'm going to use y. So I'm going to say there is some y such that, and the restrictor is patient. So y is a patient. And I use and to connect it to the main. And the main is that x queued y. Okay, let me just put it in English, then I convert it to a formula, x queued y. And for this part, x queued y, we're going to go cxy using x for q. Now, putting everything back into the main formula, we get this symbolization. For all x, if x is a doctor, then there is some y such that y is a patient and x queued y. Okay. Now let me move to the next one. You can try the next one for yourself. It's a good idea in general that stop, pause the video, and just try every one of these problems for yourself. So there is someone who is liked by everyone. So there is someone is basically saying someone, right? It's a little confusing, but it's the same thing. Someone is liked by everyone. That's what basically this statement is telling us. So here we are going to use the domain of people because we have someone and everyone. So this whole thing just basically means someone. So we are going to use an existential quantifier. And there is no restrictor predicate here. We're just saying someone is liked by everyone. This whole thing is going to be your main predicate. Okay, so how should we do this? Well, we say there is some x. And about x, we are saying, and what we are saying about x is that x is liked by everyone. So I just put it in English. X is liked by everyone. Okay, now notice that this statement here, x is liked by everyone itself, is a universal statement. We have everyone as which is a universal quantifier, and we have x is liked. Again, here we don't have a restrictor. X is like this by everyone is that main predicate. So the way that we say that, if you want to, you can convert it to an active voice instead of the passive voice, which is basically everyone likes X. And you just need to symbolize everyone likes X. So we go for all Y likes X. Okay. Now putting everything back into the main formula, we get this as the overall symbolization. We say there is some X such that for all Y likes X. So there is someone who's liked by everyone. And the domain is the domain of people. Okay, let me move to the next one. So no one loves everyone. Okay, remember that when we have no, we can just understand that as a negation of existential, right? So this is basically the negation of the claim that someone loves everyone. Okay, so we want to deal with someone loves everyone. Okay, so here obviously we are going to use existential quantifier, and we are going to use a domain of people. Again, we don't have a restrictor predicate, so this whole thing here is the main predicate. So let's deal with it. It's not the case that there is some X such that X loves everyone. And for X loves everyone, we're going to say for all Y in the domain of people, X loves Y, right? And putting all the things together, we get it's not the case that there is some X in the domain of people such that for every Y in the domain of people, X loves Y. That's the symbolization. Okay, no doctor cures every patient. Okay, again, we have no, so we can just understand it as the negation of the claim that some doctor cures every patient. So let's just deal with this existential here, then we put the negation up front. So we have some, we are going to use existential, and the sentence is about doctors, so that is going to be a restrictor predicate. And about them, we're saying that some of them cures every patient. So that is going to be our main predicate. And the restrictor and main are going to be connected through an and because we have an existential sentence. Okay, so let's start doing it. We have the negation. And then we have, it's not the case that there is some X such that X is a doctor. And then we have the main predicate. X cures every patient. Okay, now we need to deal with the main predicate. Okay, notice that we have every here, so this is going to be a universal statement. And the main predicate itself has restrictor and main. So the restrictor of the main predicate here is patient. And the main obviously is that X cures patient, right? So about patient, we are saying that X cures them. And that is going to be our main. And those two things are going to be connected using an arrow, right? Okay, so let's deal with this part. So we're going to have for all, we're going to use Y. Okay, we cannot use X because we are already in the domain, in the scope of X. So for all Y, the restrictor is patient, Px, and we use an arrow because we have a universal. And the main here is that X cures Y. So just like that. Okay, so let me put everything back together and we get the whole overall symbolization. So we are saying that it is not the case that there is some X in the domain. And what's the domain? Well, notice that people is not explicitly mentioned here. So we can use the domain of things or the domain of people. It doesn't matter. So for all X, sorry, it's not the case that there is some X such that X is a doctor, and for all Y, if Y is a patient, so I made a mistake here. So this should have been Y, not X. Let me correct this. Right? For all Y, if Y is a patient, then X cured Y. And we close it. Okay. Let's do number 8. So we have here, there's a student. There is, but just basically means some. Right, so we're going to use existential. So some student fails every exam. So if you're talking about students, that's going to be or restrictor. And about this group, a student is saying that some of them, or there's one of them that fails every exam. So that's going to be the main, and these two things are going to be connected through an AND. So for all X, sorry, there is some X such that, so the restrictor goes first, X is a student, then we use an AND, then the main is that X fails every exam. So let me just put that here. X fails every exam. Okay, now we need to deal with this main predicate here, and obviously this is a universal statement, and it's a statement about exams. So exam is going to be a restrictor predicate, and about them we're saying that X fails them. X fails every one of them. So X fails is going to be our main predicate for this part. Okay, so we're going to do it this way. For all Y's in the domain, then the restrictor is that is exam. So Y is the exam. I use E for that. Then we have an arrow and connect it to X fails Y. and for x fails y, using f for fail, we have this. Okay? Putting everything back into the main formula, we get this. There is some x such that x is a student, and for all y, if y is exam, then x fails y. So that's our symbolization. So what should the domain be here? Well, since we have every exam, we are going to use the domain of people, right? Sorry, we are not going to use the domain of people. We are going to use the domain of things. And since people is not explicitly mentioned, we don't need to worry about using the domain of things. Okay. So let's move on. So here we have a statement, and we are going to symbolize this once using the domain of people and then using the domain of things. Right? So you have a couple of questions like this on the problem set, on the homework assignment. So let's just do this one and see how it is done. So first, let's use domain of people. We have everyone, so that would be the natural choice, right? So using the domain of people. So we have everyone who meets Andy likes him, right? So the sentence is a universal. The restrictor is, it's about people who meet Andy. That's the restrictor. And the main is that, but the thing that we are saying about them is that they like Andy. And of course, we're going to use a universal. So we go for all x in the domain of people. The restrictor is that x meets Andy. Let's use M for that. X meets Andy. I use A for Andy. And then we have an arrow. And the main is that X likes Andy. Right? So that's the symbolization using the domain of people. For all x, if X meets Andy, then X likes Andy. Now we are asked to do the symbolization using the domain of things as well. So how should that go? So let's move here. This time we are going to use domain of things and symbolize this very same statement that everyone who meets Andy likes him. Now, if you're using the domain of things, you need to make it explicit in your formula, in your symbolization, that we are talking about people, right? We are not just talking about anything. We are talking about a specific group of things, people who meet Andy. Sorry. So here is how we do it. So we say for all x in the domain of things, if x is a person and x meets Andy, then x likes Andy. Okay, so this is the formulation, symbolization when you are using the domain of things. All you need to do is that if you are using the domain of things, there is going to be an additional restrictor predicate, namely people. Because the sentence is not just talking about things in general, the sentence is talking about people who meet Andy, right? So people who meet Andy. But if you're using the domain of people, then you don't need to mention people. Obviously, if you're talking about people, so you just say for all x in the domain of people, such that if x meets Andy, right? Okay. So that's it for the first part. In the second part, we are going to deal with natural deduction in first order logic. The last part of class today, we're going to talk about natural deduction in first order logic. Basically, what we're going to do is that we're going to add to the rules that we had from truth functional logic some new rules that will allow us to deal with quantifiers. Before I talk about the new rules, we need to talk about the notion of a free variable and also the notion of an instance of a quantified statement. So the notion of a free variable, it was mentioned last week in class, so I'm going to go over it real quick. So here, consider this formula. We have this existential, and the scope of the existential is the formula immediately to its right. Now, this x here and this x here are in the scope of this existential. So we say that these variables are being bound by this existential, right? Whereas here, we have existential, the scope extends to here, the x is being bound by this existential, right? But this y is not in the scope of any quantifier associated with y. So we say that y is a free variable. Contrast that with this sentence here. The scope of this existential extends to here, the scope of this one to here. And notice that this x is in the scope of there is some x, so it is being bound by this. And y is in the scope of there is some y, so it is being bound by that. So there is no free variable here. Okay, so that's the notion of free variable. We can have the same thing with universal quantifier. I'm not going to go over it because that's the same thing. Now, we can talk about the notion of an instance. So the instance of a quantified statement is what you get when you eliminate the quantifier and you replace the free variables with names. So here we have this existential, and we want to get the instances of the existential. So you eliminate the quantifier, the main quantifier, and then what you are left with is this, right? And this x and this x are free variables. Now if you uniformly replace these free variables with names, you get instances. So for example, if we replace x with a, which is a name in our system, we get fa and ga, right? We can call it the a instance of this existential. If we replace x with c, which is also a name, for example, we get fc and gc. We can call this the c instance, right? So that's the notion of an instance. So let's talk about this last one, the instances here. So in order to get the instances of this formula, we eliminate the main quantifier, which is this one. That gives us this. Then we replace free variables in this new formula with names. And here, this x is free because it is not in the scope of any quantifier associated with x, and also this x is free. Right? Y is not free, is being bound by for all y. So if we replace x with a name, we get an instance of the quantifier. So for example, if we replace it with a, which is a name, we get for all y fa arrow g a y, right? So this is the a instance of this, right? You can replace x with b, that gives you the b instance, or c or d or whatever. But you need to replace both x with the same name, right? So you cannot replace one of them with a, the other one with b. That's not how it works. Okay, now we can look at the rules. So the first rule that we're going to look at today is universal elimination. And the rule tells us that from a universal formula, you can derive any instance of it using universal elimination. So let's say that you have for all x, fx arrow gx. I mean, maybe this is the premise. The rule tells us that from this you can get any instance of it. For example, you can get the A instance using universal elimination on line 1, or you can get the B instance, right, where you replace x with B, universal elimination, on line 1. Any instance that you want, you can get from a universal. That's the rule. The second rule we're going to look at is existential introduction, which allows us to introduce an existential. And the way that the rule works is like this. It tells us that, let's say that you have a formula, for example, FA and GA. From this, you can introduce any existential that has FA and GA as an instance. Right? So for example, let's say we have this one as a premise. From this, you can get there is some x, fx and gx, because line 1 is an instance of line 2, right? If you eliminate the existential quantifier on line 2 and replace x with a, you get fa and ga, right? So from line 1, you can get line 2 using existential introduction on line 1. There are other formulas that have fa and ga as an instance. For example, here is another existential. There is some x, fa and gx. Line 1 is an instance of line 3 as well. If you eliminate the existential quantifier on line 3, you are left with fa and gx, then you replace x with a, you get fa and ga, right? So 1 is an instance of 3 as well. So if you want to, you can get 3 from 1 using existential intro. So the way that you can think about it is this. This is an alternative way of thinking about existential intro. So let's say that you have fa and ga. The idea is that you can pick the name a and replace it with x. You can do it with one x, or you can do it with both of them. So for example, if you replace both of them with x and put a existential quantifier up front, you get this. There is some x, fx and gx. If you pick only one of the a's, for example the second one, and you replace it with x and put a existential up front, you get this. Either way you think about it, the idea is that if you have an instance of existential, from that you can introduce the existential. Okay, so those are the two rules that we are going to work with today. Okay, here we have this problem. Okay, notice that here our goal is to get to an existential. Okay, that's the goal at the end. So we set up the proof the way that we did before. Premise is at the top, the goal at the end. So my goal is to get to this thing. And since this is an existential, I'm trying to introduce an existential. So my plan is going to be to use existential introduction. Now the rule existential introduction tells me that in order to get an existential, I need to have an instance of the existential. So I need to have something that looks like this. G, a name goes here, arrow, negation, H, the same name goes here, right? And any instance gives me the existential. So it could be A instance, B instance, and C, or C instance, or any other instance. However, in this particular problem, since up here we have A as a name, the chances are that we are going to work with A, right? So down here, when I am thinking what instance should I try to get, that A gives me the idea that I need to perhaps get the A instance in this particular problem, right? So that's my new goal now. I want to get GA arrow, not HA, because if I have that, since that's an instance of the existential, then we can get the existential. Okay, now how could we get GA arrow, not HA? Okay, at this point, you can think the way that we did in doing truth functional proofs. So your goal is a conditional. You can try to do a conditional introduction. However, since we have derived rules to use, I'm not going to do conditional introduction because I think there is an easier way to do the problem using the derived rules. Okay, but if you want to do that, that's fine. You can do conditional introduction at this point. But I'm going to look up and see what I have up there. Up here I have a universal. So I can do a universal elimination, which basically tells me that I can get any instance of the universal that I want to. Which instance should I get? Well, A instance, right? We're working with A. So let's get FA arrow, the negation of GA, which is the A instance of 1. And we are doing this using universal elimination on 1. Okay, now, since we have FA and we have FA arrow GA, you see that's the reason we wanted to get the A instance, because now we can use FA on line 2 together with FA arrow not GA, and that gives us not GA. Arrow elimination 2 and 3, right? Okay, but my goal is to get GA arrow not HA. Can I get it from things that I already have? Well, it turns out that I can. If you remember from derived rules, there was a rule that tells us that if you have not A, from that you can get A arrow whatever you want. The rule is called PMI. Okay. Now here, since we have not GA, we can get GA arrow whatever we want. And in this case, we want not HA. So we get GA arrow not HA from line 4 using the rule PMI. Okay, now I have one of the things that I wanted to get. I have an instance of the existential. So from that, I can get the existential. So on line 6, we get the existential because we have its A instance, and the rule is called existential intro. Okay, that's the idea. So alternatively, you can think of the rule in this way. You replace A with X and put an existential up front. So that gives you line 6. Okay, let me do one more. Okay, so here again, we have one premise, and our goal again is to get to an existential, right? So my goal is this thing at the end. And since I'm trying to introduce an existential, so it makes sense that we use existential intro. But this rule, existential intro, tells me that I need to have an instance of the existential. And an instance of the existential would be something like this. The negation of F, a name goes here, or K, and the same name goes here in this blank. Right? Now, what name should I put here? Well, notice that this problem doesn't involve any name. It's all variables, right? If we contrast this with the previous problem, in the previous problem we were given a name in the premise, namely A. And for that reason, on line 5, we decided to get the A instance of the existential because we already had A in the problem. But here, in this new problem, we don't have any name. So we can go with any instance of the existential that we want to. You can go with A instance or B instance, C instance, anything that you want to. Okay? So let's go with B. Anything works, it doesn't really matter. Not FB or KB, is the B instance of the existential. So my goal is to get this thing. Because if I have this, then I can get the existential. Now, how can I get FB, not FB or KB? Well, let's look up there and see what we have. We have this existential, and we have this universal, sorry, and we can eliminate it and get any instance that we want to. So what instance should we get? Well, since we are going for not FB or KB, it makes sense to get the B instance of this existential, of this universal. So let's get FB arrow KB using universal elimination on line 1. Okay, now does that give me the thing that I want? Well, it turns out that it does. If you remember from derived rules of functional logic, if you have A arrow B, from that you can get not A or B. It goes in the other direction as well. And this was called impla, right? So from FB arrow KB, I can get not FB or KB using impla on line 2. And now that I have the B instance of the existential, I can get the existential using existential intro on line 3. Okay, I'm going to do one more. Okay, so here we have this problem, and our goal is to get to this formula at the end. There's some x, there's some y, not fx or ly. So since my goal is an existential, I'm going to use existential intro, which means that I need to have an instance of this existential. And an instance of the existential is something like this. You eliminate for there is some x, and what you're left with is there is some y, not f, and you replace x with a name. I'm going to leave it open, or ly. So that's an instance of the existential. So my goal is now to get this thing. Of course, I need to put a name in the blank. I'll do that later. But my goal is to get this. If I get that, then I can get the overall existential at the end. Okay, now this new goal itself is an existential. So in order to get it, I'm going to use existential intro. Which means that I'm going to need to have an instance of this new existential. And an instance of this new existential is something that you get if you eliminate there is some y, and you have f, not f something, or L, and now another name is going to go in this blank here. Let me make this one red. Now this could be any name. It could be the same name that is in the first blank, or it could be a different name, right? So that would be an instance of the second existential. So now this is my goal. Okay, notice that I have left the blanks open. I need to figure out what to put in them later, but that's the overall strategy. Okay, now let's look at the things that we have up there and figure out how we can get to these things. So up there we have a universal, and we can eliminate the universal and get any instance of it that we want to. Now what instance should we get? Well, notice that we have B here, not GB. So it makes sense to get the B instance, because then we can use not GB together with the instance. So let's go for the B instance of the universal. Okay, now we can use 2 and 3 together. If you remember, we had a rule in functional logic called DS, or disjunctive syllogism. And the rule was like this: if you have A or B together with the negation of one of the disjuncts, for example, not B, from that you can get the other disjunct, right? So here we have a disjunction on line 3, and we have the negation of GB. So from those two things we can get the first disjunct. So we can get not FB using DS on 2 and 3. Okay, now that I have not FB, I can get not FB or anything we want using or intro, right? So here on line 5, I'm going to put B in this blank that I had left open. Because that way I can get 5 from 4, right? Since I have not FB, I can get not FB or anything I want. Now what should I put in the second blank? Well, I can get anything I want, and it really doesn't matter. So I can put A in there, or I can put B in there. It doesn't matter. So I'm just going to put A. Good. So from 4, we can get this new line on 5. And it's a good old disjunction introduction. Okay, now the formula on 5. So notice that I put B in the blank, so I need to put B in all the other blanks that I had as well. So now 5 is an instance of the thing that we have on line 6, right? 5 in fact is the A instance of line 6. If you eliminate, there is some Y, and then replace Y with A, you get line 5. Okay, so we're set. We have the instance. From that we can get the existential. The rule is existential intro, and we're applying it on line 5. And now the thing that we have on line 6 is the B instance of our overall goal on line 7. So we can get line 7 using existential intro from 6. Okay, that's it for today. We do more of these problems next week. Have a good one.